sketching polynomials, what we look for when we're sketching them. Now obviously, we talked about this before, the y-intercept is always the constant number, because when you sub-zero in to the x's, obviously they all disappear, and you're just left with a constant. Always easy to find. So let's have a look at this example. Now, I don't have to expand the whole thing out, because if I did, the constant number would simply be all the constant numbers multiplied together. So I know the constant number is going to be 1 times -1 cubed times 2 squared, which, if I've done that right, -4? That sounds right. Okay, so let's plot that in. There we go. Okay, we know the y-intercept's -4. The x-intercepts are the solutions to the polynomial equal to 0, what we call the roots. That's great if it's factorised, nice and easy. If we can't factorise it, then we probably don't worry about it. We might estimate, but I wouldn't worry too much about trying to find the exact location. Obviously, quadratics, linear functions are easy, but once we start getting the cubics, depends on the cubic, whether it's easy or not. But fortunately, our one is already factorised for us. So we know the x-intercepts, they'll be at -1, +1, and -2. Okay, we've got some x-intercepts. Now, dominance. When you're looking at a function, the dominant term takes over when you get out of the extremities, out at infinity. So when you're talking about a polynomial, it's always what we call the leading term, the term with the highest power. Because the bigger the number, then the higher power makes a significant difference. Yeah, when you have a small number, for instance, the difference between, well, 1 squared and 1 cubed, there is no difference. 2 squared, 2 cubed, okay, there's a small difference. 1,000,000 squared, 1,000,000 cubed, we're now getting to be quite a large difference. So obviously right out at infinity, there's going to be a huge difference. So we sort of ignore the other terms, and all we have to do is have a look at the leading term. And this curve will behave like that. So the leading term, again, I don't have to expand the whole thing out. X times x cubed times x squared gives me x to the power of 6. Now, if I had said to you, draw y equals x to the power of 6, we would have ended up with a U-shaped curve. Well, I'm only interested about what happens out of the extremities. So I know I'm going to start up here somewhere, and I'll finish over there, just like that U-shaped curve would have. All right, that gives us a bit more information. Now, you look at the individual x-intercepts, the individual roots. If you've got them factorised, that tells you a lot of information too. Because the x-intercept will behave like the power. So if I've got an even power, it's just going to come down and touch the x-axis. You know, a U-shape, just like x to the power of that even power would. So with this one, x plus 2 is squared. So over here at -2, now I know it starts up here. So it must come down and turn at -2 and go back up. So something like that. Similarly with the odd ones, they're going to come through like the cubic, that inflecting shape. So all right, we've got x minus 1 cubed. So over here at, that one would be +1, wouldn't it? Over here at +1, well, I know I finish up there, so it must come through like that, like a cubic. Now, as far as -1 goes, well, it's to the power of 1. So it'll cut through like a straight line. It'll just be simply, bang, I'll just cut the intercept. And that is, in fact, what the curve ends up looking like. So we see, oh yeah, there's the turning like the parabola. Over here at 1, there's our cubic y-intercept. Now look, this turning point down here, how did I know it was on the left-hand side? Why wasn't it on the right-hand side? Well, I'm just drawing a very basic graph. I might put it on the wrong side for now. Once we start doing some calculus, we can identify the location of that exactly. But at this stage, we're just drawing some rough sketches. So we might have it on the wrong side to start off with until we get a bit more knowledge about how to draw sketches and different tools we can use. But that's not a bad sketch. It gets the basic shape of it for us. We know what that curve's looking like. Now, if you can factorise it completely, well, then you've got one of the basic curves. That's what we saw the other day, where simply, all right, it's my x to the power of n curve, but I've just shifted it a units to the right or the left, whatever it happens to be. Now, if I wanted to solve then an equation like this one, what I could do is do it graphically, similar to what we did with the quadratic inequation. I could say, well, I'll draw this graph, and what they want to know is, for what x values is this graph below the x-axis? When is it negative? So let's draw this graph. We know we have an x-intercept at 1. There's one over there at -3. Ends up like that because x minus 1 is squared, so I know it's going to turn there. The leading term is x cubed, so if I was to draw x cubed, it would look like that. And so this one looks like that. Now there's my curve. So I don't really care about that turning point up there, because remember, we're just interested in the x-intercepts. When is this below the x-axis? Okay, well there's the key points, those boundary points. And when is it below? Well, over there, and that's all. So the solution to this would be x is less than or equal to -3. And a lot of people forget the single point. But of course, that's where it's equal to 0 as well. So we get x equals 1 as a possibility as well. Okay, so that's the